Okay. So randomized block design, extension of completely randomized design that we had before. So everything that we learned about the block is like that we want to have the randomized. Like in the previous slide, we said that randomly we ask people to, like, for example, to have your material A on the right foot or material B on the right one. So randomly we would assign it to the people. Here is the extension of completely randomized design to the situation where block effects are eliminated from treatment effects and the residuals. Extension of paired comparisons, paired t-test that we have, to more than 2 treatments or the level of the treatments that we would have. In chemical engineering applications, blocks could be different blends of the chemical, raw material suppliers, batches, substrates, days of the production, operators, raw materials with different impurity levels. There are many blocking effect that we have in our experiments when we work in the lab, and we can consider it. Right. Here is another example, which is a good one. It says that we have more than 2 treatments. So in the previous example, we had in treatments, we had material A and B. So we had 2 treatments, but here is more than 2 treatments. And determine the wear of 4 different brands of tire after 50,000 kilometers of driving. The experiment involved 4 different cars, which are the blocks. So we have 4 cars. Like in the previous one, we had 10 people as blocks. So here is that we have 4 cars. And for each car, we have tire brand of A, B, C, D that we use. So car number 1, and then we are gonna like do our measurement. And here you can see the numbers. So we would say the design involves K treatment in N blocks. So here, K and N, both of them are 4. But it's like that we have 4 different tire brands, right? So tire brands are the like the number of the treatments that we have, like K. And then we have in N blocks, N is the number of the cars that we would have. Like the same before, we had 10 people, so N was equal to 10 in the previous example. So here we have 4 cars, so N is equal to 4. So the model that we want to write it down is going to be y is equal to mu plus like beta plus tau and epsilon. So beta is block deviation from ith block, and the mu and tau and epsilon are, we had all of them before, like tau is the difference between them, and the mu is the mean, and epsilon is the, it's going to represent error here. Like we want our error to be epsilon. Epsilon means very small number that we would have. And then the equations are very similar to the one that we had before in the previous chapter. So this is the correction for the mean. For the correction of the mean here is that you would say 1 over K and K times N, like the number of the block and the number of the treatments. Like we would say number of treatments or number of the level of the treatments. In some books, they say number of treatments. I added a note at the end of these lectures. And in some books, they're gonna name it like the levels of the treatments, but they're the same. So we would say 1 over K times N, and then it's the correction for mean. So here it's very similar. We say 1 over 4 times 4, and then like the whatever y that we have, like we're gonna add them, all of them together, and then would say power 2, square it, and we're gonna find out the value for the correction of the mean. So treatment sum of a square, we would say the sum of a square, S of the treatment, it's gonna be, you can write it down SS as well. So in some books they write it down SS, in some books they write down S, but as long as we know that it's sum of the square of the, like something that we're looking for, it's fine. We would accept both way of writing. So for the sum of the square of the treatment, we would say 1 over N, and then the treatment total, whatever you have for that specific treatment, power 2, and then you would add each of them minus the correction of mean. Like for example, you would say that they had like T is equal to 1 to K. So we have 4 treatments. We would say that, okay, so the first one plus the second one, like the third one and fourth one, right? And then I would say 1 over 4. This 4 is different than this. One is for N, the other one is for K. A minus correction of mean is going to give you the value of it. Degree of freedom is going to be 3 here. And for the block sum of the squares, so we would say sum of the square of the block is going to be 1 over K. So these equations are really repetition. So we had similar to these ones in the previous chapter. But over there, we said that between treatment and within treatment. But the logic, like the concept behind it, it's going to be the same. The only thing is that we are considering blocking and blocks. So 1 over K, and then sigma I equal 1 to N. So here N is the number of the blocks that we would have, and block totals, power 2 minus correction of mean. And then for each of them, like when you add for each block, the total that you have for that block, like for car 1, the total block that you have for second, third, and fourth. So you would square them, and then you would divide it by the total number of the treatments that we have. So here we had 4 different material for our treatments for the 4 different tires, right? So we would say 1 over 4, and we found the sum of the square of the blocks. And degree of freedom of blocks is the N minus 1. So we had 4 cars, so 4 blocks. So minus 1 is going to be 3, so it's going to give us the degree of freedom. So total corrected sum of the square is the S of the total. And what are we going to do is that we would say sigma Z, like the total of the Y power 2, and then minus correction for mean. And we will just find out the value of it, which is 18.9. And then degree of freedom of it. For the degree of freedom, we have this equation. This is K times N minus 1, which is like we have like total number that you have minus 1. So we had 16 different reading, right? Minus 1 is going to be 15 here. Now with the beautiful ANOVA table that is with us all the time. ANOVA table is one of the most important tables that we have in stats. Whether you are working as a beginner, like you are working with the just simple linear regression model, or you go to the surface modeling later and optimization, you will see that ANOVA table is always there. So it's very important that we learn the concept behind the ANOVA table, because it's going to help us a lot to, like, we would shift it, move it, modify it a little, and it's going to give us the ANOVA table for blocking, or for the factorial design, like the fractional factorial design. All of those, we have the ANOVA table, and it's the same. So the source of the variation, we have here, we have the brands of the tire, right? We have different cars, which is, there are blocks, and we have error, and then we have the total. So for the sum of the square, we found out for the brands, like for the treatments, different treatments that we have, for the blocks, which is the car, and then we have the error. For error, what you can do is that we found total as well. So total minus this, and this is going to give you the error. The degree of freedom, we have all the degree of freedoms. So it's like that you would write down 3 here and 3 here. So total was 15. You will say 15 minus this 6 is going to give you 9. Mean square, it's an ANOVA table. What are you going to do is like that you're going to divide the sum of the square by the degree of freedom. It's going to give you the mean square. So we have the mean square of the brand, and mean square of the, like mean square of the treatments, and mean square of the blocks here, and the mean square of error, which is the same as the sigma 2. But look at here, here is the interesting part. For F observed, we have 2 values for F observed here. So we have F observed for the brands, and F observed for the cars, like for the blocks. And then we are going to read the F from the table. So for reading the F from the table, for F, we needed to have like 2 different degree of freedoms when you wanted to read from the table. Let's say we are working with a 95%. So alpha is 5%, and F is like gonna be 3, and then like the degree of freedom that we have for treatment or the block, 3, and then it would be for the error is 9. because denominator is always denominator is always the error. So the degree of freedom of the denominator is going to be 9, and then we have 3. We would read it f of 3 and 9 0.0 like at 0.05. F table after 0.05. So we read it F critical is 3.86. So later we're going to talk about that, but like we are going to see the situations that they're like the number of the treatments and the number of the blocks are not the same. We would need to read different value for the F critical from the table in that case. But right now, let's just compare them. So look at here, the F observed for the brands, it's greater than the F observed, critical, and then F observed for the cars with blocks are greater than the T critical as well. So let's see what's going to be the conclusion. So therefore, brands or the treatments that we have, so we said we have 4 different tires, right? So 4 different brands do not show the same amount of the wear. So the tread loss for cars or block is not the same either. So in this study, the latter is not of particular interest. In fact, it was expected. So we expected that one would happen when we were like comparing the blocks. So that's going to be the ANOVA table. So using blocks made the experiment more robust in the face of disturbances and sensitive to detecting differences among treatments, right? When we think about it.